Hello and welcome to this video on derivatives. Today we will be looking at maxima and minima. So these concepts, if you have studied physics, you have maybe heard about them already because they are used all over physics and they are important in mathematics too. So let's see what they mean. Now if you just look at the two words, you can guess that this has something to do with maximum and this has something to do with minimum. And since we are studying calculus, we have to be talking about functions. So let's say I have some function here, something like this. So this is some curve and this is my function f of x. So I have the x-axis and the y-axis here. Now what does it mean if I say maximum and minimum of this function? Now obviously if I say maximum, you can see that as x approaches infinity, the value of this function increases. So that means the maximum value of this function is infinity, and similarly the minimum value from this side is negative infinity. And this does not give us much information about the function really. So instead of looking at it as a whole, we will look at the function's behavior locally. So what does this mean? Okay, so let's say I have some point here. We call this point A, and I'll just zoom in. So here you have point A. And okay, so to look at the behavior locally means if you have a point, look at a small area around the point rather than looking at the entire function. So look at small areas and kind of break up the function into these small pieces and see locally how it behaves. So if you see here, the function you can see is decreasing in value, and so the derivative would look something like this, the tangent line I mean. Okay, so this is a tangent line at point A, and since the tangent, you can see that the slope of the tangent is negative. So the slope of the tangent is just the derivative. So at point A, the derivative of this function, so at point A, this is how we write it. This thing is less than 0. And because the derivative is less than 0, you can see the derivative always points in the direction that the function is moving, just ahead of this point. So if the derivative is pointing like this, that means the function is also decreasing as you go slightly ahead from the point A. So if the derivative is 0, that means at A, the function is decreasing. Okay, so here's where it is important to notice that I'm talking locally. So that means at a small area around point A, a small piece of the function around point A, it is decreasing. Because of course if you look here, it does decrease, but then it also increases a lot. So this derivative, we talk only locally about it. It describes the behavior of the function locally. And actually maybe ahead you'll study that there's a cool way to approximate functions which Newton invented, which goes like this, by looking at the derivative and drawing the function. So anyway, if we look at the derivative, we can tell locally how the function behaves. Okay, so now if we are talking about maximum and minimum, we are talking about it in the sense that I described earlier, that is locally. So just by glancing at this function, we can tell that around this point here, this point here, this one. Okay, so let me erase point A. At these 3 points, the function has something very special. If you look here, this point is a maximum locally. Of course, again, it's not maximum if you look at the whole thing, because this is much more than that. But locally, at a very small area, this function gets a maximum value here and then it drops. Similarly here, the function reaches a minimum value and then increases, and the same thing here. So these two are local maximums and this is a local minimum. So this is exactly what we mean by maxima and minima: a local maximum and a local minimum. Now if you see, if you draw the tangent to these points, it appears to be parallel, all appear to be parallel to the x-axis. And why is that? So it's pretty simple. Let's say that the derivative of the function at that certain point was greater than 0, so that means positive, or let's say that it was negative, anyone, as long as it's not 0. So if it's positive, that means that at that point the derivative is positive, so that means it's sloping like this. Okay, so it's facing upwards. And so since the derivative approximates the function locally, the function must also be increasing locally. So if you move slightly ahead of the point at which you took the derivative, the function will also look something like the derivative. So maybe it's something like this, slightly different. But if the function is increasing, then this cannot be a maximum, because maybe then some other point here would be a maximum, or something here. Because if the function increases just after this point, that means this is not a maximum. Similarly, if the derivative is less than 0, that means the tangent line looks something like this. That means the function is decreasing at the point. And so again, this cannot be a minimum. So this gives us a very important constraint on what the derivative can be at a maximum or a minimum, and that is precisely 0. So the derivative must be 0. In other words, it has no positive slope or no negative slope, it's just straight line parallel to the x-axis. And that's the only way we can get a maximum or a minimum. So using this condition, we can now find out at what points does the function get these maximum and minimum values. Okay, so here I have this function x square plus 1 along with its graph. So you can find this graph using a graphing calculator, or you can just draw it by yourself. So now we want to find what is the maximum or minimum value of this function. So just by looking at the graph, we can easily tell that it's here. This is the minimum value, because all other values of the function are above that. But we want to find exactly at what point is this, and this is what you cannot tell just by looking at the graph. So what is this point? Namely, what are its x and y coordinates? So just by looking you can tell that its x coordinate is 0, but what is its y coordinate? That we need to find, and so this is a good way of finding it. So if you remember, the previous condition was just that you take the derivative, so the derivative of f of x, and you set it equal to 0. So that means I have to take the derivative of this function x square plus 1, set it equal to 0. Now this is a pretty simple example. So we have just 2x and the derivative of 1, which is a constant, is just 0 and is equal to 0. So x is equal to 0 by 2, that is equal to 0. And of course this we already knew, that x must be equal to 0 because we can see it from here. But now we want to find the y coordinate. So if x is equal to 0, then what is f of x? So it's just x square plus 1. So that's 0 square plus 1, and that's 1. So finally we know that at 0, 1, that is this point here, So this point is actually 0, 1. So this is 1 unit high from 0. At that point, this function attains its minimum. So this is how you can find the maximum and minimum. Let's see another example. So before moving on to another example, we did find the point, but we still don't know, if we don't look at the graph, we still won't know whether it's the maximum or minimum value of the function, because the condition for both is the same, and so we don't yet know whether this is actually a maximum or a minimum. So how we do that is by using the second derivative of the function. So as you know, the second derivative gives us concavity. So if I look at this function here, it looks something like this, and this is the derivative here, it's equal to 0. Now, so we had found the derivative of this function. So the first derivative of f of x was 2x, and if we graph 2x, so this is just a straight line passing through the origin. If we graph the function of the first derivative, and we can actually see that this is always increasing. This function is always increasing, 2x. And so the second derivative of f, so f double prime, is greater than 0. And so this means that it's actually concave up, the function. So although here at this point it is 0, we know that in the future it's going to increase because the second derivative is positive. So if it's 0 here and it's going to increase in the future, that means definitely this is a minimum. On the other hand, if the second derivative of the function is less than 0, then we know that it's concave down. So it's actually going to decrease. So temporarily the derivative will be 0, and then the derivative will become negative. That's what the meaning of the second derivative is. And so that means that this point was actually a maximum, because the function will now decrease. So that's how you tell if it's a local maximum or a minimum. So in this case, definitely it's a minimum, because the second derivative, that is, so if you take the second derivative of f of x, that will just be 2. And since this is positive, we know that the function must be increasing afterwards. And so this point is actually a local minimum or a minima. Okay, so here we have the following example, and we are going to find the maximum and minimum of this function without using its graph. So this is going to be interesting. Okay, first of all, we find the derivative. So that's 15x square plus 6x, and this thing is just equal to 0. So now I can just factorize it. So this is what I have, is equal to 0. Okay, so this was the derivative actually of the function. So f prime of x is equal to, and remember that we set this equal to 0 because we wanted to find the points at which the function has its maxima and minima. Okay, so from here I get two values of x. One, directly x is equal to 0, and secondly x is equal to minus 6 by 15. So if x is any one of these two values, this equation will be satisfied. Now I'll go ahead and find the second derivative of the function, because I want to be able to tell the difference between the points which are maxima and minima. So the second derivative is just the derivative of the first derivative. So I have 30x plus 6. Okay, and at x is equal to 0, so when x is equal to 0, the second derivative, so if I just plug in 0, will give me, so I have 6, and when x is equal to minus 6 by 15, the second derivative of the function is, as you can see, since 15 and 30 will cancel to give 2, So I'll have minus 12 plus 6, that is just equal to minus 6. So the values are not actually important. What we just need to see is that the first derivative is the second derivative is greater than 0, and here the second derivative is less than 0. So if I continue writing here, so the point corresponding to where the first derivative is greater than 0, okay, so at x is equal to 0, this point will give me what? And here I have minus 6 by 15. So where the derivative is greater than 0, I'll have a minimum, and where it is less than 0, I'll actually have a maximum. So this, if you remember, is because I explained before this. So if I have a minimum, that means the function will actually increase. Okay, so now after I have found these, I'll go ahead and find the values, the y values of corresponding to these two x ones. So when if I put x is equal to 0, I have just equal to 1 here, and when x is equal to minus 6 by 15. Okay, so this value you can probably calculate by yourself, so I'll just write down what it is. So this, okay, so this is the value, and this is simple addition. You can calculate it, the value, the exact numerical value by yourself. And so altogether what we have is that at the point 0, 1, this function f of x, so f of x has its minima, and at the point minus 16 by 15, comma, and whatever was the value of that expression. So I'll just write down the entire expression for now. Maybe you can simplify it later. So this entire thing is the y value. F of x has its maxima. And so now, as you can see, without using the graph, we have found the points. So at this point, so if this is a graph, at this point 0, 1, the function has its minima. So that means it's decreasing here. So probably locally it looks something like this. And at this point, minus 6 by 15, so this is of course negative, and let's see, this thing should be positive. So somewhere around here it has its maxima. So probably something like this. Okay, so of course I have not drawn the graph accurately because I don't know the values of these, but you can do. And this is all for today. So let's see. Yes, I've covered everything. So if you understood everything that was taught, don't forget to like the video, subscribe to the channel, and also share the video with people to whom it might be useful. And thank you, and I'll see you in the next one.